So let's start by putting in the information for the 50 Newton force to the right. That's so easy, as I've said already. All of it acts in the horizontal direction, so all 50 newtons of it acts horizontally, that's the magnitude. And then instead of writing to the right, remember we decided that to the right is going to be called positive. So that positive has nothing to do with magnitude, it's telling us the direction. None of it acts in the plane that we have called vertical, and so it has no vertical component. Now let's deal with this more difficult force, 40 newtons at 140 degrees to the 50 Newton force. So here we've placed our two vectors on the Cartesian plane, and we're going to focus on this force now. So we construct a right-angled triangle, even if not to scale, but just in our rough diagram to help us to understand. We construct this right-angled triangle, and that helps us to see the x component of this 40 Newton force. Then we can construct another right-angled triangle, and that helps us to understand the vertical, the y component of this 40 Newton force. Now I've just removed the Cartesian plane background because as long as we understand that it's there, we don't actually need to draw it in. The important part of it that I haven't removed is that we've decided that this direction to the left is negative, and we've also decided this direction, which is not actually down, it's actually out of our picture, is also negative. So both the horizontal and vertical components of this particular force are negative. That doesn't mean they are less than 0 in magnitude. It just means that the directions are what we had called negative in each of the dimensions. Now we need to put information in that we know about the direction of F. And we know that the 40 Newton force F acts at 140 degrees to the 50 Newton force. And we know the 50 Newton force acts along the x plane, the horizontal direction. But now more useful for us would be this angle here. We know that Fy is along the y-axis of our Cartesian plane, and Fx is along the x-axis of the Cartesian plane, and those two axes are at right angles to one another. So it's very easy to see what this angle here will be. It must be 140 degrees, which is the whole angle, minus 90 degrees, which is this right angle triangle, and that leaves behind the angle that is useful to us. 140 minus 90 is 50 degrees. So we know that F acts at 50 degrees to its y component. And since this is a right angle triangle, always the horizontal and vertical components are at right angles to one another. The two must add up to 90 degrees, which means that this angle here to the horizontal is 40 degrees. So now we have all the information we need to calculate the horizontal and vertical components of the 40 Newton force. Let's start off with the horizontal component. Remember that cos 40 is adjacent over hypotenuse. The 40 degree is adjacent to Fx, and the hypotenuse of course is F. And we know F's value, it's 40 newtons. So we can just rearrange this, multiply both sides by 40 to clear away the fraction. And in this way we can find the magnitude of Fx. So Fx is equal to F multiplied by cos theta. F is 40 newtons, theta is 40 degrees. So we have 40 multiplied by cos 40. On your calculator, type 40, then type cos. Multiply that by 40, and you should get 30,64. Obviously, the unit is newtons. So we've calculated Fx here, and we know that it's 30,64 newtons. From our diagram, we can see that it's pointing to the left. And remember that we decided that to the left is negative. So instead of writing to the left, we replace this to the left with a sign negative. So Fx's value is minus 30,64 newtons. Remembering that that minus doesn't mean it's smaller than 0. It means it's pointing to the direction on the x-plane that we had chosen to be negative. In other words, left. So we put that information in here. That is the horizontal component of this 40 Newton force. Now we need the vertical component of this force. Remember that vertical vertical in this case is not meaning up and down, because that would not have been helpful here. It's meaning into and out of the page. Not sure if that's very clear, but towards us or away from us. That is what we're referring to in this particular case, because then it's useful to explain the other dimension of this force. So here we have our diagram again like we had before. Let's calculate this in two different ways. First of all, let's use cos 50 degrees. We know that cos means adjacent over hypotenuse. In this particular case, the 50-degree angle is adjacent, is touching Fy. So for cos 50, adjacent over hypotenuse is Fy over F. And of course we know that F is 40 newtons. We multiply both sides by 40 to clear the fraction. So we have Fy is equal to 40 cos 50 degrees. And you should find that your answer is 25,71. And we see that the direction looks like it's downward. Of course it's not. Remember from our picture of the tree, we're looking from the top. Here's the tree and we are looking down on the tree. So this is not really a downward direction. It just means out of the page, out of the picture. And we have said already that out of the picture is going to be represented by the negative sign. So that's why we say that Fy has a magnitude and direction of minus 25,71 Newton. Magnitude 25,71, direction minus. In other words, out of the picture. Now let's solve this in another way. Instead of using cos 50, let's realize that this angle here is 40 degrees. How do we see that? These are alternate angles. These are parallel to one another, and so here we have a Z shape. Alternate angles are always equal. So now let's use that 40 degrees there, and let's use sine 40. Now remember that sine always means opposite over hypotenuse. And for this particular case, sine 40, the 40 degrees has Fy opposite it. And of course, F is the hypotenuse. Magnitude of F is 40 newtons. We multiply both sides by 40 to clear the fraction. So we get Fy is equal to 40 sine 40. Put this on your calculator and you will find the same answer as what you found before. Again, 25,71, and the direction again is negative. We put that information in here. 25,71 Newton magnitude, direction is negative. So now what we've done is we've found the horizontal and vertical components of each of the two forces that are actually acting on this tree. But how does that help us? Remember, we are actually trying to find the resultant. So we must add these up to find the resultant's X component. We must add these two up to find the resultant's Y component, and then we can use these two, add them together, vectorially that is, not algebraically, to find the resultant itself. So let's do that. First notice that I've replaced this vector here rather by its two components. These are its two components. That one went there and that one went there. In effect, I've also replaced this vector by its two components. That one went there and this one's 0, so of course it doesn't go anywhere. So my diagram now shows only the components, horizontal and vertical. And when we have only components, then everything lies on either the x-axis or the y-axis. And then we can add and subtract algebraically for things that are on the same line. And for things that are perpendicular to one another, we can use Pythagoras and trig. So let's do that. So remember, we are trying to find the resultant acting on this tree. Let's begin vertically. 0 Newton plus minus 25,71 Newton is equal to minus 25,71 Newtons, of course. Notice these we can now add algebraically because they all lie on the same line, the vertical line, the y line. Now we get to the horizontal components. They also lie on a single line, and so we can add them algebraically. It's obviously going to be to the right because the force to the right is greater than the force to the left. That plus means to the right. So can you see that we've actually replaced the real vectors the real forces that the men were pulling with two forces that have the same overall effect as those men. But the nice thing about these two forces is that they act at right angles to one another, making it easy to calculate their resultant, their vectorial addition. We don't need to draw a scale diagram. So here they are, and they are at right angles because one is a vertical and the other one is a horizontal component, which are always at right angles to one another. So now we need to find their resultant. So how do we add these two vectors? We need to move one of the vectors so that its tail is on the head of the other. It doesn't matter which one you move, and we move it down to the head of the 25,71 Newton vector. Notice that that angle will also be in 90 degrees. And then all we need to do is complete the triangle. Put in the resultant. Remember that this angle is 90 degrees. And can you see that we can solve this now using Pythagoras? Because we know with Pythagoras, radius or hypotenuse squared is equal to x squared plus y squared. We know the magnitude of x, we know the magnitude of y, and so we can calculate the magnitude of the resultant. So we do that. Pause this while you check that your calculation is right. You must be used to using a calculator correctly. It's very easy to make mistakes with calculations. But remember that the resultant is a vector. So it doesn't only have magnitude, it also has direction. So we have not finished yet. But because this is a right angle triangle, we can make use of trig. That angle there is theta, and so we can make use of tan theta. Now let me just explain. Tan theta always means opposite over adjacent. Now opposite isn't always x or isn't always y. It depends. And in this particular situation, the value opposite to theta is what we might call x, even though often we would call opposite y and adjacent x. So please do be careful of this. Y over x is only tan theta if theta is the angle to the horizontal. If theta, as in this case, is the angle to the vertical, then tan theta is x over y, not y over x. So let's substitute into this. So you would first put this into your calculator. Then you probably have to press shift, and then you probably have to press the button tan, but you won't be doing tan. Above there you will see tan to the -1 probably written in yellow, and shift means that you're now going to use that function, and tan to the -1 means that it tells you the angle associated with that, which is what we want. We want the angle. But if we think back to our tree, we have these two forces acting, and we've just found the resultant, and this angle 37 whatever degrees is to that y plane that we've got over here coming in out of the picture, and that's not really so useful. It would be more useful to be able to indicate the resultant as an angle to that green vector. Let's rather complete this right angle triangle and find out what is that angle there, because then we can say that that's the resultant's angle to the horizontal, or let's rather say to the 50 Newton force that's acting in that direction. And of course it's really easy to find what this angle is, because it's 90, which is the whole here, minus just this little part, which we can round off to 53 degrees. And before we go, have you already liked? Have you subscribed? Have you left me a comment? And please go and visit my website. You'll find a lot of resources there, and they're categorized in a way that will make it very easy for you to find what you need. Until we meet again, learn science!